All right, we have a sailboat is sitting at rest near its dock. A rope is attached to the bow of the boat, is drawn in over a pulley that stands on a post at the end of the dock that is 5 feet higher than the bow. So we have the boat's bow, sailboat, and 5 feet above that on the dock, there's a pulley where the rope is attached to. The rope attached to the bow. The boat is drawn over the pulley, drawn in. The rope is being pulled in, and if the rope is being pulled in at 2 feet per second, that there is a rate, the length of the rope, dt. So we can't use that until we've taken a derivative. And the 5 feet we can use because that doesn't change. The distance the boat is from the dock, we don't know, but that changes, so we're going to have to use a variable like x. And we want to know how fast the boat's moving in, so that would be dx dt. So the relationship between x and L, the length here of rope, looks like a right triangle. So it would be the length of the rope squared would equal 5 squared plus x squared. And if I took the derivative of this becomes 2L dL dt equals the derivative of 5 squared is 0, and this would be 2x dx dt. So they ask us to figure out if dl dt is changing at 2 feet per second when the boat is where is it? How fast is the boat approaching the dock when the length of the rope from the bow to the pulley is 13 feet? So L is 13. And so we need to know X also. So 13 squared is 169. 5 squared is 25. So 25 from 169 is 144. So X must be 12 feet. This length is 12, this is 13, and this is 5 at a moment in time. Now we can't use that early on, we can only use it now that we've taken the derivative. And we know L, the 2, this number, the 2, the X, we just need to find this. So it's going to be 2 times 13 times 2 feet per second divided by 2 times 12, and that will be how many feet per second the boat's speed coming in. So 4 times 13 divided by 24, and we get 2.16 feet per second. That's how fast the boat's going to be coming in. If the rope is coming in at 2 feet per second, the boat's going to be coming in at a little bit faster. Okay? So we have the swimming pool. 60 feet, 25 feet, varies uniformly from 3 feet to 15 feet. Suppose the pool is being emptied and has been emptied and is now being filled with water at a rate of 800 cubic feet per minute. We want to know at what rate is the depth of the water measured at the deepest point of the pool, so from here up to water level, increasing when it is 5 feet deep at that end. So if this is 5, and this is not going to be 60 necessarily, 5, and if this is 3, it won't be, because there would be still 10 feet here. So it's way down here. 5, this might be 10 feet, and 3 more feet for the whole, I don't know, 5, 10, 5 feet here. So this ends up here. Anyway, so this is 5 feet, but this is changing, so we can't use it. We have to call this maybe H for height, and we can call this X, and we need to know the volume of this slice, because we have a change in the volume per minute. So we got to figure out the volume of that. So we have similar triangles here. At 12 feet, it's 12 feet deep. It goes right to the bottom there, and that's the same shape as this triangle. And we need to find the volume of this. We need to know the height, the width, and this depth. And we're going to take half of that, because that's half of a box. So the ratio between this side and this side is the same as 12 to 60. So we're going to call this the height, I said. So H2X is 12 to 60. See, 12 goes into both of those. That's 1 to 5. So the volume is H times X times 25. But we need to know how the rate of the water is changing. So we need to get the X out of here. And so we can solve for X. If I multiply by X and multiply by 5, I get X equals 5H. So I put 5H in there, and my volume is 5H squared times 125. And now I can take and find the rates. dV dt is, let's see, 5 times 125 is 625. Derivative of h squared is 2h dh dt. So, increasing at the deep end over a time period, describe how the depth of the water will increase at an increasing rate, at a decreasing rate, or at a constant rate. The depth will go up quickly here because it's not doing very much volume, and slow down until we get to here, and then it'll go at a constant rate. But we need to find the rate at which the depth of the changing when it's at 5 feet, so we can put 5 in here. And the volume is 800. This is in cubic feet. Everything's in feet, so we're okay. We don't have to worry about our units. So if h is 5, 2 times 5 is 10. 10 times 625 is 6250. And we divide that into 800, and we'll find out how fast the height is changing. 10 times that is 6250. And the height is changing at 0.128 feet per minute. Okay.